Hello. In this video we are going to take one final look at the Carnot cycle and arrive at what is one of the pinnacles of human thought, the second law of thermodynamics. Without further ado then, let's remind ourselves of what we have learned about the Carnot cycle thus far. I have explained how a Carnot cycle can be used to describe the set of transitions that take place in particular special types of engines. I explained how these engines are driven by the changes in state that happen inside the gas within the pistons inside them. Furthermore, I told you about how the gas inside these pistons was a one-component, one-phase system whose state at equilibrium, in accordance with Gibbs' phase rule, can be characterized using two thermodynamic variables only. Throughout the previous videos, I used the pressure and the volume to characterize the state of the gas inside the piston. I thus drew our thermodynamic cycle on the PV plane and explained how the system, on completion of a cycle, returns to the initial thermodynamic state. In terms of the operation of the engine and the set of transitions inside the gas, I said there were four stages. During the first of these, the engine is placed in contact with a heat bath and the gas is expanded isothermally, i.e. at constant temperature. During the second stage, the heat bath is removed, the system is thermally lagged, and the gas is expanded adiabatically. During this second step, the thermal lagging prevents heat from being exchanged with the surrounding, and thus the temperature of the gas drops. In the third step, the system is placed in contact with a heat sink, and the gas is contracted isothermally. The heat sink is then removed, the thermal lagging is placed around the system once more, and the system is compressed adiabatically so that the temperature of the gas increases back to its original value. I have shown that the Carnot cycle is useful because it allows us to give a precise definition of temperature. We know that heat is absorbed from the heat bath during the isothermal expansion stage of the engine's operation, and that heat is released to the heat sink during the isothermal contraction stage of the engine's operation. We further know that the amount of heat absorbed and released during these two stages is the same for all Carnot engines operating between the same two temperatures, as if it were not, we would be able to create thermodynamic cycles which would transfer heat from cold bodies to hot bodies with near zero net work expanded, which we said was impossible. We thus define temperature using the Kelvin scale shown here, which tells us that the ratio of the temperature of the heat sink to the heat bath is equal to the heat output to the cold sink divided by the heat absorbed from the heat bath. Throughout my videos, I have explained that the Carnot engine is special, but have not really dwelled on the reason why. In the last video, during which I talked about the definition of internal energy and the first law of thermodynamics, I explained what made the Carnot engine so special. The key thing is that the set of thermodynamic transitions that take place in a Carnot engine together comprise a closed loop around state space. The initial state of the gas in the piston is thus equal to the final state of the gas in the piston, and as such, because the first law thermodynamics tells us that the internal energy is a function of state, the total change in internal energy that occurs when the Carnot engine completes a cycle is equal to zero. The last thing that I have used the Carnot cycle to introduce is the notion of entropy. I said that entropy is an extensive thermodynamic variable and that this variable, like the volume or the internal energy, is a function of state. As such, the entropy change that occurs as I move from state A to state B only depends on the states that I am moving between. It does not depend on the pathway that I take between the two states. A nice experiment to do is to draw the set of transitions that occur inside the Carnot engine in the TS plane rather than the PV plane. When we do so, we find that the set of transitions looks something like this. During the isothermal and expansion and contraction phases, the temperature of the system is held fixed, So these transitions correspond to the horizontal lines in the rectangle shown in this figure. The vertical lines, by contrast, correspond to the adiabatic expansion and contraction stages. Remember that adiabatic means that heat is not transferred to or from the engine during these stages, as the system is thermally lagged. We have learnt that whenever heat is transferred to or from a system, the entropy of the system changes. Hence, during the adiabatic transitions, when no heat is transferred, the entropy stays fixed. Let's now move on to the subject of this video, the second law. We have said that the Carnot engine is special because the gas inside its piston moves around a closed path in state space. This ensures that the change in internal energy, which we have denoted delta E here, is equal to 0, because remember, the internal energy is a function of state. What this implies in turn is that all the heat absorbed by the system from the heat bath is either converted into useful work or is dumped out into the sink. In real engines, this is not likely to be the case. It is not that energy will not be conserved, it is rather that large amounts of energy will be expended in what I call uninteresting machine-related nonsense. Examples of this being friction, leakage of gas from pistons, the heating of various components in the engine, and so on and so forth. We thus replace the equality sign here with an inequality to reflect these unfortunate and wasteful uses of energy. When we now rearrange the top inequality and divide both sides of it by a factor of QH, we get the following new inequality. This expression essentially tells us that the Carnot engine is the most efficient engine that there is. This seems reasonable. The Carnot engine does not engage in nonsense like friction and so on and so forth, which means we get the maximum amount of work out of this engine for a given amount of heat input. We now recall the Kelvin definition of temperature, which tells us that if we take the heat input from the hot bath and divide it by the heat output to the cool sink, this is equal to the ratio of the temperatures of the heat sink and cold bath. This allows us to replace all factors of QH in the above inequality with THs and all factors of QC with TCs, as shown here. We now think about the efficiency of our real-life engine with its insistence of engaging in machine nonsense such as friction. We know that for our Carnot engine, the efficiency, delta W over QH, was given by QH minus QC all divided by QH. We then further note that the efficiency of our real engine will be less than this. It thus stands to reason that if we write the heat absorbed from the hot bath of our real engine as QH prime and the heat output to our new engine sink as QC prime, that we can write the following inequality. I have rewritten the inequality that we arrived at the end of the last slide at the top of this slide, although I've got rid of the prime symbols as they're no longer necessary. A simple manipulation of this equation gives us the following. We can now rearrange this to give us the result shown here. This result makes physical sense. QH over T minus QC over T will be less than 0, suggesting that the engine will output heat to the universe. Friction does indeed cause things to heat up, and so this is consistent with what we would expect based on our experience. The result that we have arrived at here is enormously important. We can write it another way as follows. The result is known as the Clausius inequality. It tells us that the integral of the heat input into the system divided by the temperature around a closed loop is less than or equal to 0. Heat is thus not a function of state, as the integral of this quantity around a closed path is not guaranteed to be equal to 0. On going around a closed loop, the system will either output some net amount of heat to the universe, or it will output no heat to the universe. We can arrive at the second law of thermodynamics by starting out from the Clausius inequality. Remember that this result tells us that the integral of dq over t is less than or equal to 0 if we go around a closed loop in state space. For the purposes of this demonstration, we will consider a loop that goes through the 2 points A and B. In going from A to B, we will take the red path, in which the heat output plus the work done will not equal the change in internal energy. On the red path, there is some other hidden process, such as friction, that sucks away internal energy. On returning to B, we will take the black path, for which the heat output plus the work done does equal the change in internal energy. We can now write the integral around the closed path as the sum of these two line integrals that take us from A to B and from B to A. Furthermore, we know from the Clausius inequality that this whole integral will be less than or equal to 0. Let's now look at the second, black term in this expression. We are told that for this path, the change in internal energy is exactly equal to the sum of the work done and the heat output. In other words, we have an accurate mathematical description of all the processes at work during the transition represented by this path. Based on the logic in my video on the internal energy, we can thus replace the dq in this integral by a TdS, as shown in the top right of this slide. The t's in the numerator and the denominator then cancel, and we are left with the integral of ds. If we reverse the limits in this integral, the integral changes sign, so we can get to the result shown here, the integral between a and b, the integral of b and a, the integral between b and a of dq over t is equal to minus the integral from a to b of ds. We can thus write the final value of this integral here as the change in terms of the change in entropy in going from A to B, which we indicate here using the symbol delta A right arrow B of S. Remember though that this works for the black path because we know that the heat output plus the work done is equal to the change in internal energy. There are no processes that are hidden and that we have not mathematically quantified. Substituting the result that we have arrived at in the top right-hand corner of this slide into the inequality, i.e. replacing the black integral, we get to the following result, which, when rearranged, gives us our statement of the second law of thermodynamics. The change in entropy in going from state A to state B must be greater than or equal to the integral of the heat output in undergoing this transition divided by the temperature. In summary, the main result from this video is the statement of the second law that we have arrived at here. If we consider an isolated system which does not exchange heat with its surroundings, we can set the right-hand side of this inequality equal to 0. We thus arrive at a perhaps more familiar statement of the second law of thermodynamics. We can express this in words rather than mathematical symbols as follows. The entropy of an isolated system increases during a spontaneous change. This is a monumental statement. Remember that I said in the first of these videos that physics is an attempt to answer an ancient question on the nature of change. I want to remind you of this now to underscore the magnitude of what has been achieved in writing down the first and second laws of thermodynamics. The laws of thermodynamics are in essence stating that all processes that happen in the universe, in short, all the changes that are possible, have two common features. They conserve the overall energy of the universe, and they cause the entropy of the universe to increase. In short, In stating the laws of thermodynamics, we have provided an answer to this ancient question. All the changes that are observed in the universe have these two common features. And on that profound realization, I will thank you for your attention.